Electronegativity values came about by a guy called Linus Pauling. He realized that the homonuclear bonds, such as these ones here, so the 436 and the 159, so if you average those bonds together, you should get a HF molecule. You should have something about this strong, 297. And it's actually much stronger. It's 567. And so the idea was there is, in this bond, there is one of these things pulling electrons to itself, creating some polarity. And so one of them is more positive, one of them is more negative, and that causes an extra attraction and strength between the two. And so we did lots of experiments and used experimental data, which you will actually do yourself when you do the energetics topic. So heats of formation, bond energies, and a few other types of enthalpy values. And he came up with this formula that works out what electronegativity is. He just assigned the greatest value was 4, which happened to be the fluorine atom. So that's why we have such a strange definition of electronegativity, which is a measure of the ability of an atom to attract bonded electron pairs to itself when in a covalent bond. So in a covalent bond and bonded electron pairs. So why not just say it's the ability of an atom to attract electrons to itself? And that's based, it's this here, bonded electron pairs to itself in a covalent bond, because that's where the experimental evidence comes from. And so he worked out the strongest one was fluorine, which is 4. I think 3.8 is, or something gets rounded off or something. It's so they are a little bit arbitrary, but we'll just go with these numbers that come from your data book, and you'll get the general pattern that goes along here. And so you can see that these ones are a lot stronger, and these ones are the weakest ones over here. Not very good at drawing electrons to themselves. Okay, so the general trend is electronegativity increases across the period as the nuclear charge increases within the same shell, same distance to the electrons, therefore attraction increases. So you can see this is across a period, same distance. This is in a covalent bond. These two are joined to each other. This one's got a stronger nuclear charge, so it will draw the electrons to itself better. Now, if these two are joined together and then we're going down a group here, this one has increased shells, and so the ability of this nucleus to attract the electron is far weaker, and so electronegativity decreases as you go down the period. And so we should expect top right hand corner is fluorine, which is the greatest electronegativity, and bottom left is cesium, which has very poor ability. So when you're looking at these things, this is actually very useful in determining generally whether it's ionic covalent or a polar. So if you grab the molecule's electronegativity values from the data table, which is, this is not the IB one, but they are about the same values. I haven't cross-checked exactly every value, but what you'll find is there's some magic numbers you need to learn. If the electronegativity difference is greater than 1.8, it's ionic. If it's less than 0.4, it's covalent. And if it's in between, you'll call it polar covalent. Now you need to know those because they will help you later on in determining lots of other things.